Hello, everybody. Thank you very much for joining us for this session on carbon capture. There have been a lot of ambitious climate targets set by Japan, by China, by a number of corporates in the last few months. So we're very, very glad to have with us one of the foremost experts on carbon capture, Brad Page. Brad, you started your career in the energy sector in Australia. You're now you've spent the last 10 years as CEO of the Global Carbon Capture and Storage Institute, and you're also on the UK government's Carbon Capture and Storage Council. So welcome, Brad. Welcome from Australia. We're delighted to have you, and excited to get through some of the questions on this very, very important technology in getting us toward net zero. So I think, since we may have some generalists on the line, Brad, it'd be great if you could just outline what carbon capture is as a technology, and really the objectives and the development of the global CCI over the last decade.
Well, thanks, Shamini, and thanks very much for the opportunity to be here. I'm a bit troubled by your introduction. I guess after all this time, I may be viewed as an expert, but I think there are others that could equally claim that. Carbon capture and storage is really a suite of technologies that come straight out of the oil and gas industry, and it's a value chain. So first of all, you need to capture the carbon dioxide, and that's done in a variety of ways, but generally some sort of chemical process to capture the CO2 molecules out of usually an exhaust stream of some sort. From there, that CO2 is then usually compressed, dehydrated, cleaned up, and put into normally a pipeline where it's transported a variety of distances, sometimes extremely short, other times up to several hundred kilometres, maybe more, and is then re-injected at least 800 metres underground into suitable rock formations. So we're not talking about caves and caverns, we're talking about the pore space in porous rocks. And in fact, the geological structures look extremely similar to what oil and gas is extracted from. And so really, enhanced oil recovery is where the technology first comes from, where the upstream oil and gas industry is expert at stripping out the CO2, discovered quite a long time ago, many decades ago, that if you took that CO2 and re-injected it into a depleting oil reservoir, you could re-pressurize that reservoir and push more oil out. And in the process, the CO2 predominantly stays trapped as it displaces that oil and stays underground. So in very simple terms, that's what CCS is. In terms of its applications then, it's moved on way beyond the oil and gas industry. And essentially anywhere that you find an exhaust stream with carbon dioxide that's rich in it, you can actually apply this technology. And so it's moved on from a narrow view of just EOR to being actually a climate change technology. Sorry, and then the next question was, what about the Institute? My apologies. So the Institute's 10.5 years old now. It was established by the Australian government with some very generous seed funding. It's not a government agency. It's been right from the start a company, not for profit, registered in Australia, owned by its members, and we're very unusual in that our membership includes national governments, some provincial governments, most of the large multinationals you'd expect in the oil and gas industry, especially. Original equipment manufacturers, some research institutes, and a couple of NGOs as well. So we are a very, very broad church in terms of the ownership, 70 odd owners around the world. We're headquartered in Melbourne, Australia, but we also have staff and offices in Tokyo, in Beijing, London, Brussels, and Washington, DC. About to appoint somebody sometime soon, I would expect, in Houston as well. So very, very much a global operation, and we have one sole objective, and that's to accelerate the deployment of CCS. And why would we do that? Solely to address the climate challenge. That is the only reason. So
yeah. Okay. Daunting. You've estimated that by 2050, I think you sort of projected that we would need around 2,000 CCUS facilities in order to sort of be tracking towards Paris targets. And my understanding is that we're somewhere around 19 at the moment. What needs to change? What are the levers that you hope to bring to bear? And, is that target really achievable?
Yeah, so let me update a couple of the numbers, just because, we're monitoring them all the time, so I guess we know. So at the moment, there's 20, and we only track commercial scale operations, by the way. There's lots and lots of pilot and demonstration and research CCS projects. We're aware of them. We look after and focus on the big end of all of this in the commercial scale. So there's 20 of those operating today. There's actually 21 constructed. We've got one at the moment that's in mothballs because of market circumstance. There's another 20 that are in various stages of construction or advanced planning. So, there's a pipeline here as well. Those 20 operating today are capturing and storing around about 40 megatons of CO2 per annum. Now, if you then look at what the IPCC's 1.5 report says, if you look at what the IEA modelling says, you've actually got to scale it up 100-fold by somewhere around 2040 to 2050. So we're talking about going to 40 gigatons, 1,000-fold, not 40 megatons, but 40 gigatons. And we're actually these days thinking more in terms of volumes rather than individual facilities. And Shamini, you're right. We said exactly what you've said there. I'm just sort of taking you to the place we are today, where we actually think that most of the individual facilities, for reasons of economies of scale, actually need to be bigger than we had previously talked about, and our previous experience was. So really 1,000-fold, 40 megatons, 40 gigatons we've got to get to. Now, what's standing between us and getting there? Well, fundamentally, it's much the same as what's standing between us and getting there for almost any of the climate change mitigation and abatement technologies, because whenever you look at all of the work that's done by independent analysts, and they have no bias about individual technologies, nothing much is on track for net zero by mid-century. So we come back to all of the time, we need to have very clear government policies that back in and give you a pathway to that net zero commitment that governments were giving as part of the Paris Agreement, and also the objective of at least 2 degrees C and below, and the below is generally regarded as 1.5. So the first thing that's got to happen is government policy that gives you a pathway there. And the next thing that then has to follow on from that is that I think, as everybody knows, greenhouse gas emissions are a classic case of a tragedy of the commons, that nobody owns the atmosphere, and as a result, people pollute at their will and without penalty. And until we actually impose some sort of value around CO2, that's going to continue to happen. And that value can take a variety of forms. You can price it, you can regulate it, you can give tax credits, you can do lots of things, but it's got to have a value. And I think that's the next thing. And we haven't really seen in broad scale across the world this sort of application of a value to CO2, and nor at the sort of levels that are going to be required to achieve net zero emissions. So it has to be an economic reason to do this. And then from there, there are a bunch of things specific to CCS that are going to be important. Some of the things that are important here are around actually accelerating some of the models that are now quite clearly the best way to go with this, which are known as hubs and clusters, which is where you see a clustering of emission-intensive industry, not terribly far generally as it happens from a good storage site. But nobody is necessarily prepared to move to put in place that transport and storage infrastructure. But if you got governments and you got the private sector together to create common user infrastructure, and that actually removes one of the big issues. So there's a real push on now, and we can actually see 15 of these hubs and clusters around the world starting to come to the fore, and many of them are backed by governments, and they are going to be critical to unlocking carbon capture and storage into the future across its very wide range of applications. And then I think the next element that we need here is we know that storage is not an issue. The world has more storage, geological storage, than is needed by factors of 4 at least, and probably more. What we do need, however, is a lot more work that characterises that storage in various countries to a much finer degree, so that it removes some of the risk of somebody trying to develop a greenfield storage site. We know, for example, in North America, there's extremely good knowledge right throughout the USA, very good knowledge throughout Canada, not bad knowledge actually through Mexico, and it's actually why you see the most CCS projects coming into being in both the US and Canada in particular. Good storage in lots of other parts of the world, not necessarily as well understood. So there's an opportunity to do some things there. And then I think finally, like all abatement technologies, we've got to continue on down the research pathway to keep pushing the boundaries of what's possible to find better efficiencies to lower cost. But of course, lowering cost is dependent on a market being there. You don't just keep toiling away at the bench to discover that there's nowhere to then deploy your latest invention. So I think there's a whole bunch of things in there, and of course there are many others, but I think they're the key things that at the moment really need some more attention if we're going to move forward.
Well, that's interesting. I mean, you talked about cost. I mean, when we look at decarbonisation, our oil and gas analyst, Michele Della Vigna, there's obviously the easy decarbonisation, which is the first half of emissions, then there's the more challenging. And as you mentioned, CCUS is really targeting that more challenging portion of emissions. And you mentioned the cost. I think my understanding is that carbon capture is priced between $20 and $100 at the moment per metric ton. What do you think, if you could take a stab at this, what do you think the potential price path is for this technology, and when could we have more widespread commercial adoption? And also, if you could sort of, with that adoption, in which industries?
Sure. So you've asked pretty much the normal question everyone asks, and it's the one that has the normal answer of, well, it depends. So the cost actually depends hugely on the application. So let me explore that a bit for you. If you were to look at any industrial process where there is a very, very high concentration of carbon dioxide delivered as a result of that process, then actually CCS becomes much, much cheaper straight away.
Right.
Best example of that, oil and gas. So gas processing necessarily, as part of that process today, strips CO2. And it strips CO2 in very high volumes, good purity generally, but there is still some cleanup, and is part of the process. There's no add-on cost. What's often done then is it's just vented to atmosphere, when in fact the other option is to dehydrate, compress, put into pipes generally, and store it. And so, in fact, some of the lowest cost opportunities sit in oil and gas processing in particular. So that's why that if you go to our status report, which you can get online, you'll see that we've got a great bubble chart there, and it is dominated by gas processing for CCS, and that's because it's really cheap. The carbon's captured already. You need to do a bit of cleanup, you stick it in a pipe and you put it in the ground. And in many cases, that's under $20 a US dollars.
Okay.
Why isn't it done more? Very, very simple. Why incur $20 a ton if you don't have to? Now, that's changing. That's changing. Look at the number of the oil and gas companies that have committed to net zero by 2050 for their own businesses, for scope 1 and scope 2, and in some cases, scope 3 emissions as well. They are going to move down that path for sure to actually deal with that. But government policy has a role to play here as well. So, that's one example. Biofuels is another good example. Ethanol is a great example of where CO2 is emitted, captured, very easily dealt with. So it's another example of very low cost opportunity for dealing with. If we go out to the opposite end of the scale, cement processing, very difficult. The calciners emit huge amounts of CO2, but it's diffuse. It's in a difficult to capture process. It's probably well over $100 US a ton to actually capture. There's quite a bit of work going on in that area. This is an area where we're seeing a lot of research and development activity and some novel technologies coming forward. And so Calix is a company that is working in Belgium at the moment, building a completely different style of plant that captures CO2 from cement manufacture at much lower cost, as an example. So it's not as though nothing's going on, but there are those applications that actually are just a walk-up start, pretty straightforward. And then there are those applications where there's a lot more work to be done yet to actually move that cost down. But even at $100 a ton, when you go and look at some of the more commonly deployed abatement technologies, including renewables, for example, because of the way that incentives and price structures have been put in place through government policy generally, quite often, not universally, but quite often, the actual avoided cost of the CO2 emitted is pushing up around $100 a tonne from many of those programs. It's just it's expressed in a very different way. And it has government policy to actually bring forward some sort of rectification of that missing carbon value. So all these things keep going back to, we've really got to get in place not just the objective of net zero, we've got to get in place the right policies that bring forward all the appropriate technologies and properly value CO2 so that we deal with it in an efficient way. So there's no one single price for CCS. It can be sub $20 US a tonne. It can be $100 and more dollars a tonne, depending on what you're trying to capture and where you are in the world. It can be very sensitive to electricity price because of the large scale compression that's required as well. So it depends.
Really varies.
Come back to my first answer.
So yes, so you've consistently sort of mentioned policy and policy and a price on carbon as being critical. Are those the major risks to carbon capture getting off the ground? Are there any others that investors should be thinking about?
I don't think they're the sole risks. I think I'd regard policy and a value on carbon as probably the enablers for the acceleration. I think after that, some of the issues that are then associated around rapid deployment of CCS come down to a need for better appreciation across a wide group of stakeholders that carbon capture and storage is predominantly a greenhouse gas abatement technology. It's not a technology to shore up and keep the fossil fuel industries going, a criticism we hear all the time. Right. It's not a technology that somehow is make-believe and a fantasy. It just isn't. There's 20 of these plants in so many different applications running today. Most of them with some form of government support, admittedly, but then so too has just about every clean energy technology got that today, and it's necessary. What I think we have to do is we have to start helping people to understand that the pathway to net zero emissions is actually a very, very complicated pathway where renewables are hugely important but cannot do it on their own. Where electrification is going to be the predominant approach to addressing this, but it can't do it on its own. It can't do it in really high heat needs. And when you come to talking about, for example, hydrogen replacing fossil fuels, then we also know that by far the cheapest way to create clean hydrogen is to take natural gas or coal and either gasify it or go down a steam methane reforming path with CCS and deliver clean hydrogen at, depending on where you are, but as a general rule, somewhere around a quarter to a third of the cost of renewables with electrolyzers. And the other thing people often don't understand, this comes from the IEA's chief economist, you know, to create green hydrogen, that is from renewables using electrolyzers, at the level it's forecast to be demanded by 2050 by the IEA, you would actually have to have installed renewables delivering the total volume of electricity in 2050 that is generated from all sources today in the world. Right? That is a mind-numbing number to think about. Renewables just to make hydrogen would have to deliver the same amount of electricity as we get today from every form in the world. So we've actually got to start understanding that the path to net zero needs everything, not just renewables, not just electrification, hydrogen from both renewables and from fossils with CCS. And then we're going to have to move into the actual carbon dioxide removal process, where nature-based solutions will be important, but many of them can't be guaranteed to be permanent. Living in Australia, I can assure you, and really, really regrettably, the equivalent of a full year's emissions went up in smoke literally earlier this year in Australia in our bushfires. Direct air capture and bio energy with CCS, both are viable, long-term and permanent carbon dioxide removal approaches. So I think it just goes to underline we're going to need all of these things. We can't just be picking and choosing, and we need to collectively as a society and across all groups understand that that's the only way we're going to get to net zero by 2050 or even any time in the second half of this century. I guess that's the real point, isn't it? We've got to get to net zero.
We do, indeed. I mean, you know, there's a lot of bubbling sort of controversy in some quarters about carbon capture, and you've referenced that storage underground is not the gating factor here. Do you see a future where the captured carbon dioxide could be used to generate materials of some value or to reverse engineer fuels rather than to be sort of stuck underground? Is that a sort of evolution of this technology?
Absolutely, and in fact, there's plenty of activity in that space today, and there are already products that are being produced, including by some of our members, directly doing those sorts of things. A couple of observations about them, though. As a general rule, and I'm not a scientist, but I am advised, as good politicians will tell you, I'm told reliably, going down a synthetic fuel path, generally speaking, means that the volume of energy that you've actually got to put into that process is greater than the volume of energy that you are going to create at the other end. That there are some serious laws of physics that are challenged when going down there. Now, that's not to say you shouldn't continue to pursue those, and it's not to say there isn't a future there. It's just to say there are some speed limits effectively around it.
Yeah.
I think the other thing that we'd observe is that when it comes to utilisation, there are some fantastic opportunities out there in concrete, in aggregates, in all sorts of things, and we support every single one of those going ahead in a sensible fashion, so long as they permanently remove the CO2 from the atmosphere. Great outcome. The trouble is that any time you look at how big can those markets be versus how large is the volume of CO2 that, frankly, at the end of the day, really has to be dealt with by carbon capture and storage. They're small. They're just really small. And so you have this hangover and this balance of excess CO2 that has to go somewhere else. And the only sensible place to put it is back where oil and gas came from, effectively. So in other words, it's geological, it's return of the CO2 to the geosphere from which it came. Because we need to remember that this problem hasn't come from the biosphere, and certainly hasn't come from the atmosphere or the aquasphere. The issue is extracting this out of the earth, and there are completely viable ways to return it to the earth where it can be locked up.
Excellent. I want to end, I guess, on a positive note, despite all those rather sobering points that you've made. You know, you touched on it a little bit in the previous response, but if you were to pick what could be the biggest technological breakthrough in carbon capture and storage, would it be a better sorbent? Could it be more efficient venting? Or is it just scale and standardization? Where do you think that opportunity could be?
Well, what we do know is that outside of those industrial processes where they're delivering a very pure stream of CO2 as part of their process, that the biggest single cost for just about everything else is capture. Very, very similar and stable costs and mature technology actually on pipelines, on compression. They're really mature technologies. Storage, you've just got to do locally. So its cost is going to vary according to where you are in the world. But capture cost. And I think capture cost is where there is the opportunity globally to see improvements. And I think what's often misunderstood or not simply not known about is the massive amount of progress that's already being made there. And, you know, we don't have time for me to catalogue everything because, believe me, there is a lot going on. But if I point you to one really great example here, and it's a company called Net Power. 8 Rivers Capital is behind it. It is a completely different technology, invented by Rodney Allen out of the UK, and effectively what it does and it has many applications. But if we just looked at it in the power sector, it can take any sort of carbon-based fuel, gas, coal, probably biomass as well, and put it through a process where instead of using those fuels to heat water, to create steam, to drive a turbine, and all of the efficiency losses that come with that, it actually goes out through an oxycombustion process and uses the concentrated high pressure, near pure CO2 to drive the turbine, and the CO2 then comes out the other end, ready to go into a pipe at high pressure. That is changing the whole scene on the cost of capture and that whole process. I'd suggest it's worth people's while going and taking a look at the Net Power website. Now, this has been demonstrated in Texas already, big demonstration plant that's operated. And Net Power now, as I understand it, is building 3 units elsewhere in the United States on a commercial basis. This is the sort of technology that is the game changer around carbon capture and storage, because it's dealing with the biggest single challenge in many applications, which is around the cost of capture. And so, as I say, it's not advertorial, and I'll let people go and look for themselves and ask questions of 8 Rivers. But the sorts of numbers that are quoted for CO2 at pipeline entry are down around $20 a tonne and less, depending on what exactly is the application, and noting that this is what's called a polygeneration plant. It delivers not just electrons, it delivers all manner of chemical and gas products as well. So it is a quite exceptional technology that's now starting to get rolled out. And it's but one example of where we're seeing lots of new investment and breakthrough technologies that I think are going to change the game around CCS.
Well, that's very exciting, and I hope that that you're right, and I hope that you're right in time. Thank you very, very much, Brad, for your time. I think I've taken away the sobriety of the complexity to net zero, and the need for policies and the need for carbon prices, and I hope that we'll get some of those initiatives from Japan and from China in the coming weeks and months. Those would significantly increase my optimism that we're, potentially headed on the right track. It's great to hear about the opportunities that we're seeing in tech innovation, and I look forward to speaking to you again, hopefully in another year or two, and we can discuss the progress that we've made. So thank you very, very much for your time, and thank you everybody for joining us.
Thanks, Sharmini. It's been great.